Hi everyone, my name is Sophia Pedigo, and today we're back with the fifth part of a series in which we've been deriving the temperature profile that varies with time for a specific material. In my last video, we did perform de von Neumann stability analysis on an equation I had derived previously. And we did this because when we coded the solution out in Python, we got a super wonky answer as soon as the R value changed to anything above 1/2. Now what we're going to be using is the Crank-Nicolson method, and this is an alternative method that gives us a temperature profile, and we're going to use this method to get the temperature profile. But before we do that in Python in my next video, I'm going to perform a von Neumann stability analysis on this guy up here, so we can prove that it's actually stable for values of R over 1/2. Or I guess really any values of R. So we've got this equation here, and basically what it is it's essentially the very similar equation to the one we used previously, except for the temperature profile, we're taking the temperature of the specific node that we're at, and we're also taking the average of, well, let me write it out. So if we've got this piece here, and we've got different little increments of this node, what we're doing is we're taking the average. If we were trying to find the temperature profile for this third little increment here, which is labeled 2, we would be taking the average of its temperature profile plus the average of the temperature profile for the next increment. So that's the basis of the Crank-Nicolson method. And what I'm going to do next is we're going to rearrange this guy so it's a little bit easier to look at, a little easier on the eyes, if you will. And then we're going to apply the von Neumann stability analysis to it so we can prove that it is stable for values of R that are bigger than R is equal to 1/2. So I'm first off going to take this 2 outside. And that's going to be what we call R. If you remember in the video where I derived the other temperature profile equation that we looked at, I was calling this guy here R, which was equal to the heat diffusion coefficient multiplied by the change in time and divided by the distance squared, x value squared. And now what I'm doing is I'm just calling R that same thing, but it's going to be divided by 2 in addition to delta x squared. So that's what's going on here. And we're going to start by grouping all of the temperature values at time n plus 1 on the left-hand side, and all the temperature values that it's just at time n on the right-hand side. So let's go ahead and do that. We're going to end up with, and keep in mind, I'm going to be writing this thing as R. Let me actually just write it down really quick. My marker's kind of running out here. This is just going to be equal to R there. I just want to make that very clear so when you see me writing R, it's not super confusing. But anyway, let's get into it here. And again, I'm just grouping the temperature profile terms at time n plus 1 on the left side, and the temperature profile terms at time n on the right-hand side. All right. So now that we've got that part done, not super difficult, if you'll recall, in one of my previous videos, we had, or actually I think it was the very first video, we had looked at a set of functions. It was like e to the ix, e to the I kx multiplied by e to the negative alpha k squared t. Um, we had proven that that was a solution for our temperature profile equation. So I'm going to be substituting that in for our values of t. And I'm going to go ahead and do that. And then once we substitute that in and rearrange some stuff, we're also going to use Euler's formula to make a substitution for that nasty little e to the ix, because that will help us simplify things even further, which is nice. So when we do this, we're going to end up with oh, and also if you look at this in each of these terms, there's a t j to the n plus 1, so I'm just factoring that out of this just so you know what's going on. Might run out of room here, but hopefully not. Okay. Kind of close there on the end. But essentially what I've done here is using that equation that I derived in the first video and I proved was going for any value of k, which is just any integer, it's always going to be a solution for our temperature profile equation. So I just substituted that in, and I also factored out on this side the temperature at position j at time n plus 1. And on this side, I factored out temperature at position j at time n. Now, if you remember Euler's formula, let me write it down here if I remember it correctly. It's going to be e to the I x is equal to cosine x plus I sine x. We're going to be applying that same formula to all of our values of e, except instead of using I to the, or e to the ix, we'll be using either e to the negative I k delta x or e to the I k delta x, just depending on where or what sign I guess we have. And so that for cosine is an even function. So when we have that negative sign, it's not going to change anything for the cosine. But when we have the negative sign, it'll make this sign negative when we're doing that. So I'm going to make that substitution now. So it's going to end up being, oh, and I'm also going to divide both sides by this whole chunky term here. And we're just going to isolate this guy here. So that's what we're going to do. So we're going to end up with tj to the n plus 1 is equal to, yeah, it's tj to the n plus 1, sorry. And then we'll have the tj, the temperature profile at point j at time n. And we're going to, like I said, substitute Euler's formula in, and we're dividing both sides just so you know what's going on. And when we do that, we get this. Next, what we're going to do is we're going to officially look at this using the von Neumann stability analysis to see if it is actually stable, because that's kind of the whole point of this. It's all fine and dandy if we've got this nice Crank-Nicolson method, but that doesn't actually help us unless it's stable for values of R that are above 1/2. So that's really what we're looking at here. And we really only care about this, or we don't only care about this part, this section here, but it's an important section because essentially is what's happening is for whatever number we have here, we're multiplying this temperature profile. And in the previous method we used, when that was happening for values of R that were higher than 1/2, this temperature profile was just shooting up and it was super big, and it was not stable. So we want to make sure that we're not multiplying the temperature profile by something really big on this side. We want to make sure that we're multiplying it by something that's, not going to make it like grow exponentially and be super huge. So what we're going to do is we're going to say, we're just going to look at this part here and we're going to kind of simplify it too. Because really, it looks like there's a lot going on here, but we can basically simplify this so it turns out to be, if we write it down, and here I've just kind of factored some things out and I'm just writing, or I'm really just writing this chunky guy up here. The cosine is y because it's just kind of messy, and I think it's a lot easier to see this. But the point is, when you have with this, you're never going to have like a super big number, and so it's actually going to be stable for any value of R, unlike when we were using our previous method. And for any value of R that was higher than 1/2, you would just get this absolutely wacky looking plot. But for this, we're not going to, because it's a negative sign up here and a positive sign down here, you're never going to end up with something super big. And so it's not going to cause that crazy looking plot that we had in the previous video. So with this in mind, what we're going to do next is we're going to use the Crank-Nicolson method to essentially do what we did before in Python, but this time obviously we're switching the methods and we're going to have a more stable analysis when we do that. So that'll be my next video.